Hey everyone, welcome back. In this chapter, we will apply the concepts we learned previously to writing code that builds something inside of Maya. We'll start by learning how we can use Maya commands inside of Python. Then we'll take a look at some of the commands I use most frequently. After we learn some commands, we'll revisit earlier chapters and see how we can apply our knowledge of Python to recreate some of the steps we took manually. Before we move on to scripting the ARM rig, we'll also write some simple helper scripts that we can add to our shelf. Alright, let's begin. To build anything inside of Maya with Python, the very first thing we need to do is import the Maya commands Python module. This will allow us to handle most of the commands that Mel uses. So up at the top of your script, you'll want to include this line: import maya.cmds as cmds. Let's test this out by converting some Mel into Python. I'll create a sphere and copy the Mel command down into my script editor. In Python, the syntax is a little bit different than Mel. We can see here that the Maya command is polysphere. To use that in Python, we say cmds.polysphere open and close parentheses. If you run this as is, it will use your defaults that are saved in your tool settings. Inside the parentheses, we will put any of the arguments associated with this command. Let's convert some of these arguments into Python. If you don't know what they mean, an easy way to find out is through the quick help. In Python, we don't use the dash to represent an argument. Instead, we write the argument followed by the equal sign. You can use the long or short name, but when handing off code to another user, it's good to use the long name in case they don't know the simple form. When an argument like x is here requires more than one value, you can pass it in as a tuple or a list. For arguments that require a Boolean value like construction history, I prefer to use true or false rather than a 0 or 1 because the syntax highlighting for true and false gives me a better idea of what data type the argument is looking for. And usually towards the end of a command, it's good to give whatever you're creating a name. Most commands have this argument. Okay, cool. Now we have written a Python command that creates a sphere based on arguments we provided. How can we call upon this sphere we just created? Well, give it a name, so we could refer to it just by the name. However, when I build anything with a script, I like to store that in a variable. So if we add our sphere equals in front of our command, now our variable has the same name as our object, though they do not need to match. If we run our command, then print our sphere, we can see that this command returns a list. There are two things in this, our sphere's transform node and the construction history node. Hold on to that thought for a minute. Let's say we now wanted to do something like set attributes on the sphere. To do this, we can try using the setAttr command. I usually take my variable and concatenate the attribute name, followed by a comma, then my value. We'll get an error doing this because our sphere is a list. To get the first item in the list, we could say our sphere 0, but if I know I'm only ever going to call upon the first item, I could put the 0 at the end of our command. That way it only returns the transform name. Usually when creating objects, I prefer to have them not return as a list, unless I want to manipulate them both in some way. Those are the basics of using Maya commands with Python. Now that we know how to format a command, let's take a look at some others that I use frequently. To demonstrate this, let's loop through the creation of 12 spheres. So let's add our command under for I in range 12, and we'll slide this over by highlighting it and pressing tab so it becomes part of the for loop. Also, because we're creating multiple objects, it's a good idea to give them some nice clean naming. Using format, we can give it a unique name using the range number, +1 because it starts at 0, and using the :02d, we can give it number padding. Whenever I move something in space, I almost always use the xform command. With it, we can manipulate our objects in several different ways. For example, I'll use it to move our pivot up, and then I'll also use it to rotate our object. So we'll say cmds.xform, our variable name. Then we want to xform in world space, so we'll set that to true. And what are we xforming? The pivot. So we'll give it a world space position. Now that we moved our pivot up by 10 units, let's set up some rotation. I want to rotate each sphere a little bit more than the last, so we complete a full circle. To do this, we can calculate the increment by dividing 360 by the number of objects we're using. Then we'll use our xform command again, but this time we'll use the rotation argument. We can even do a little bit of math inside this argument. So let's say set rotate z equal to the rotate increment multiplied by I, which starts at 0 and increases by 1 each time through the loop. So now if we remove our old sphere and run this, we get a bunch of spheres rotated around a fixed point like a clock. Another command I use all the time is the list or ls command. There are a lot of different ways you can list or filter objects with this command. Let's start out with a basic list by using a wildcard. Inside of a string, you can use question marks to represent a single character each, or you can use the star symbol to search for any number of consecutive characters. For example, sphere question mark geo is going to return the same thing if I do a ls on sphere underscore star underscore geo. As you can see over here in the quick help, there are a lot of arguments associated with this command, but don't worry, I probably use less than half of these. This is a good place to look when you want to filter something specific because naming may not always be the best option. Let's go ahead and group all the spheres together inside a variable using another common command, cmds.group. Then the object, or in this case list of objects, and just like our sphere, let's also give it a name. Now when we run this, our spheres get added inside of a group, and our variable, allSpheres, returns the name we gave that group. Another command I like to use is called listRelatives. One way it can be used is to find or list what lives in our hierarchy. So for this loop, I'll iterate through everything that is inside of our sphere group variable. This will print every transform inside the group on a new line. We can also use listRelatives to list the shape nodes of a given object. In this example, I know that each sphere only has one shape node, so I don't want my shape variable to return a list. To do that, I'll just put a 0 in brackets so only the first item is returned. Now when I print this, it shows me that S returns the transform node and SHP returns the shape node. Next, let's do a little exercise where we put a joint at the center of each sphere. Then let's try aligning the joint's orientation to that sphere. If you're feeling bold, pause the video and try doing this on your own first. An easy way to find the center of a shape is by creating a cluster. By default, the handle will be at the object's center. We will use the cluster command, and in parentheses we'll put our object. I know this returns the deformer in the handle. I also know that I only need access to the handle, so I will return the second item in the list. Many commands in Maya are queryable. To query is to ask. This means you can use query to ask the command information about something. We want to query, what is the world space position of the cluster's rotate pivot? While we're asking questions, let's also query the rotations of our sphere. We'll store this in a variable as well. We'll use the pose variable to position our joint, and the rot variable to orient it. The next command is the joint command. By default, this will create a joint and parent it under anything you have selected or whatever the first argument is. If we set the first argument to none, it will not parent our joint. You can position a joint directly in the command itself. We'll also name it based on our geometry. Let's just replace the string GEO with JNT. Then, to match the orientation of the sphere, we'll use the xform command yet again. Only this time, we'll not be using the query flag. We want to use xform directly to set our joint rotations to the variable we defined by querying our sphere's rotation. We can delete our cluster using the delete command because we're only creating this to find a position. Once we have our position, we no longer need the cluster. The last thing we'll do is bind our sphere to the joint. To do this, we can use the skin cluster command. We put the joint in first, then the object, and we will bind to selected bones. I'll run this a few steps at a time just to show what is happening for each block of code. When I run this first line, you can see the clusters are positioned at the center of each sphere. Then you can see when I run the next part, we're positioning the joint where the cluster is. Next, if I run everything together, the joints are placed, the clusters don't show because they've been removed, and then there are spheres that are bound to each joint respectively. In the next lesson, we'll take a look back at some assignments from the previous chapters. This time through, we'll be completing them with Python. Thanks for watching, and I'll see you in the next one. Hey everyone, welcome back. Do you remember the gear assignment from chapter 1? Let's open that back up. In this lesson, we'll solve the assignment, only this time, we'll do it with the press of one button. Whenever I'm trying to automate something, it helps to look for patterns that we can use. That's just one of the reasons to have good naming standards in place. Let's start out by building a list of all our gears using the ls command. Next, let's throw this into a loop and use enumerate to assign a value to each item in our list. We don't need to make any connections for the first gear, so let's skip that by saying if I is greater than 0. I is our enumerator value and it starts at 0. In other words, the first time through the list, our first gear, nothing happens. To make things easier, when I created these gears, I added a hidden attribute where I stored the radius value. I called it radius. Let's create a variable for this value, and we can define it by using the getAttr command. We We know that each gear will need a double linear node. To create a node, we can use the create node command. We can also store this in a variable. Let's give it a name that corresponds to the geo we will connect it to. To do this, we'll use the string replace method to replace the text geo with MDL. We'll want to connect this double linear node into our gear. But wait, don't we need to reverse the direction on some of these? That's right. So how can we determine which values we'll want to inverse? We can check if our value is divisible by another value by using the modulus or remainder operator. This basically says if I is not even, then let's define our multiplication factor as 1 divided by the radius times -1. Otherwise, we won't multiply by -1. Now, let's connect the rotation of the first gear into the input 1 of the multiply divide node using the connect adder command. So we give the full object name plus the attribute name first, then the node and attribute name we are connecting to second. Next, we can set the double linear's input 2 attribute using the set adder command. The value we want to put there is our multiplication factor that we just defined. And last, we'll hook up the output of our double linear into the rotate z on our geo. So again, our first gear is driving the rotation on all the others. So now, if I open my node editor, I'll go ahead and run this. You can see it's creating some nodes and making some connections. If I graph these, you can see my entire network. Now let's take a look at the gears. When I rotate the first gear, the other gears are driven and they're rotating in the proper direction. So not too bad, right? Let's take a look at another lesson. Go ahead and open up your bike rig that has all the constraints. We're going to find all the parent, point, and orient constraints in your scene. We'll loop through them, investigate the connections, then print out the command we would need to recreate that constraint. Then we can copy and paste those commands somewhere in case we need to automate this part of the rig build. The first thing we'll want to do is build up the lists of constraints we want to print out commands for. To do that, we can use the ls command with the type argument. So for parent constraint, we say cmds.ls type equals parent constraint. And we can do something similar for the other constraints we want to print. Next, let's loop through our list of parent constraints. For each constraint, we'll create an empty list for translate and rotate. We're going to check to see if there are any missing transform constraints for each axis. To do this, let's look at the connections coming from the constraints constraint translate and rotate attributes. We can do this with the list connections. We can also open up the node editor and graph our constraint. And you can see here that these attributes are connected to our driven object. I'll go ahead and copy this list connections command so we can check for the constraint rotate connections as well. Then we'll check to see if the list connection variable is an empty list. If it is, that means when we built that constraint, we told it not to connect this specific attribute. So we can append these attributes to a list that we can then use when writing our constraint command's skip argument. Next, we'll use the parent constraint command with query equals true to ask it what targets are driving this constraint. I know we only set up one target, so I'll return the first item in the list. I also know that the constraint naming is predictable, so to find the driven object, we can just replace underscore parent constraint 1 with an empty string. The last thing we'll want to do for this loop is print out the constraint command. We'll start out by opening our quotations and write the command for parent constraint. Then we can use the escape characters to add in quotes we want to print. We'll surround some curly brackets with the escape character and quotes. This way it prints out our variable inside of the single quote characters. Using dot format, in this order, we'll add our driver, the driven, our skip rotate list, then the skip translate list. Now if we run all of this, our loop prints out the command for all the parent constraints in our scene. We can copy these from the script editor history and paste them somewhere off to the side to use later. I actually just noticed that our script printed out 3 times as many constraints as there are in our scene. This is because we actually have 2 loops. We loop through all the constraints, and inside that loop, we also loop through x, y, and z. If we select our print function and hit Shift-Tab, we can move this up to the first loop. Now when we run this, it only prints 1 statement for each constraint, and not 3. So let's go ahead and copy this over, then we can do the same thing for point and orient. Instead of rewriting my loop 2 more times, I'm just going to copy the one for parent constraint and paste it, then rework it a little bit to work for the other 2 constraint types. So for orient, I'll remove instances of translate And I'll also change the name of the constraint types. Instead of skip translate, skip rotate, we can just use skip. And that will work for point constraint as well. And of course for this one, we'll change rotate to translate. So now when we print each code block, we'll get a list of orient constraints and point constraints. And I noticed that on the second one, I forgot to change my point constraint name, so I'll go ahead and fix that, and now we have all our constraints. Because we already have constraint lists defined, we can use them to delete all our constraints. So let's use the delete command, and inside the parentheses, we'll put the name of our constraint lists. Then, when we run this, all our constraints will be removed. To get them back, we can run our constraint script that we just generated. In the next lesson, we'll take a look at how we can write some useful helpers for our shelf tools. Thanks for watching, and I'll see you there. Hey everyone, welcome back. In this lesson, we'll take a look at some of the helper scripts I've included on the shelf so far. Let's start with some easy ones, and then we'll take a look at something a little bit more complex. One thing I'm always doing is zeroing out my transforms. So let's go ahead and make a helper to do that more easily. First, let's create a function and call it resetTransforms. For the argument, we'll just say nodes. For this, we can pass in a list of nodes we want to apply this action to. We can then say if not nodes, so if we pass in false for the value of nodes, then we'll define nodes by listing what we have selected. In case one were to use this function by passing in only the name of an object and not a list, we still want this to work. So we can check if the variable nodes is a list by saying isInstance variable name list. Then we can redefine nodes by putting it in between two brackets. The last thing we need to do now is loop through the nodes in our list and set the translate, rotate, and scale on each one of them. I'm just going to fix a couple typos in the script here. Then I'll create some spheres and set transform values on them. Now I can select some of these spheres and use our script to move them back to their default position. Remember, if we want to use the selection, we'll have to set nodes equal to false. Let's make another helper. Here's one we can use to either transfer pivots from one object to many, or we can use it to return all the pivots to the origin. Let's name this function transfer pivots. We'll give it one argument called origin, so we have the option to move pivots to the origin instead of to an object. Next, let's get our selection. We can then say if origin, so if we set origin to true, then we will use xform to set the pivot of our object to the origin. If origin isn't set to true, we want to move all the selected object's pivots to the first in the selection. To do this, we can record the first object's pivot by querying its world space position with xform. Then we'll loop through all our objects except the first one. To do this, we can say for s in cell, open bracket 1, colon, and then close bracket. This will be our list without the first item. Now, using xform, we can set each object to match the first object's pivot that we just defined above. Let's source this function and copy the command below. Now I'll select some spheres and run it. After running, you can see that the pivot has now changed to match the pivot of the first object. If we do this again, but set origin to true, then when we run, all our sphere's pivots will move to the origin. I have most of my helper scripts saved in a folder called nmrig inside my Maya version scripts folder. Inside this folder, I have a Python script containing node text called init.py. This file is used to mark the directory as part of a Python package. This is useful when building a more elaborate set of tools that work together with one another. It makes it easier to import and use tools from your package inside other scripts or packages. For example, if you look at my shelf command for transfer pivots, it's not the script we just wrote. I'm importing this from inside my scripts directory by saying import nmrig.shelfutils as nmutil. Shelfutils is the name of the script where my function is saved. I'm then reloading it in case I make changes to the code outside of Maya. Then run what you imported the script as, the function name. You can add right-click commands to your shelf by going to the pop-up menu items. Give it a name and then add the script you want to run when you access that menu item. This next helper script I want to show you is very important for rigging. I use this technique all the time when matching a curve's orientation to the joint it will be controlling. This script is unique to me because it includes the first Maya 2020 specific functionality that I've ever written. Don't worry if you're on an earlier version of Maya. We will write our script in a way that will work for both versions. Usually when you create a control, you want to have its orientation match the joint that it drives. However, you do not want to have any transform values on the control. To do this manually, I'm going to create a NURB circle for my control, then I'll press Ctrl G to group it. Now the control, the group, and their pivots all live at the origin. I'll select the joint, then the group to align them with the parent constraint. Instead of going through the menu, I'll type it in the Python command line down at the bottom. We say cmds.parentConstraint, open and close parentheses. Unless you set maintain offset true here, it should remain off. I also don't want to keep the constraint after it is created, so I can piggyback the delete command by putting the constraint inside of it like so. If I run this, the group will snap to the joint and the constraint will be removed. Having the default transform values will make it easy for animators to reset their rig's position. Before I show you the utility to automate this concept, let's write a little function that will be used inside of a larger one. Let's call this reset to origin. As the name implies, it will take our control or node and move it to the world origin. I've added an argument called nodePose, so we have the option of providing the coordinates. It's false by default, so if we don't pass it in, we'll just use xform to find that automatically. Next, let's freeze only the transform value by using the makeIdentityMaya command. This is the same thing as saying freeze transformations on translate only. Now that our translation is zeroed out, let's offset it to the origin. To move it to the origin, we'll need to take our node's position and multiply each value by -1. Let's put this position value in a variable called nodeOffset. We can do this in one line by saying open bracket p times -1 for p in nodePose, close bracket. This concept of making a new list based on the values of an existing list is called list comprehension. We can now use this variable inside of xform to move our control to the origin. Once our control is at the origin, we'll zero out the rotation values and freeze transformations again. This time it's okay if we set rotate equal to true. Now I will create a new control and move it away from the origin. Then I'll just copy the function name and paste it down here so we can run it independently. I'll also use my first selected object as the node I passed into the function. Be sure to actually source the function before trying to use it like I just did, otherwise you'll get an error. Once you properly source the function, running it will move the control to the origin as promised. Now let's write a more robust function that we can use to align our local rotation axis from our control to our joint. Let's name the function align LRAs for local rotation axis. We'll give it 2 arguments. SnapAlign will move the control from anywhere to the joint. With it set to false, the control will not move, but the pivot will still match the joint. Delete history will ensure that we remove history on the control. First, we can list our selection in a variable. Then, ensure we have at least 2 items in our scene selected. Our first selected object we can define as our control, and the second will be our joint. If the control we're aligning has a parent object, we'll need to approach this differently. So let's check if that's the case. If it is, we want to unparent the control using the parent command with world equals true. Next, we want to store the joint matrix, then the position and rotation of both the joint and control. We can do all this by using xform with the query argument. This next part uses a pretty cool new attribute in Maya 2020, the offset parent matrix. Using the objectExist command, we can check if our transform node has this attribute. If it doesn't, we'll have to use an offset group to position our control. The first thing I'll check is that the offset parent matrix is in its default position. To do this, I'm just going to create a new locator and query, then print its matrix so that I can copy its value into my setAttr command. Also, you get bonus points if you notice that I forgot to add the objects we're querying in our xform block of code above. Then, to set a matrix attribute, we say type equals matrix. Using the previous function we wrote, let's direct our control to the origin. Now let's set the control's offset parent matrix to the joint matrix value we have stored. Now let's take a few extra steps if the control we're aligning is a child object. This may be a little confusing, but will hopefully make more sense when we test this out. We'll start out by creating some temporary joints. One to represent our control and one for its parent. The first joint will have no parent, and the second joint's parent can be the first joint. Then, using my A to B helper provided in the shelfutils Python file, we can snap these joints into place. The temp parent joint to our parent node, and the temp child joint to our joint. We'll then parent the control back to its parent node, and use our reset transforms function to zero out any transforms. Using get and setAttr, we can set our control's offset parent matrix by copying the child joint's matrix values. Then it will be safe to delete our temporary joint chain. Now we can go back by 2 indentations and write our else condition for Maya 2019 and below. Here we'll start by moving the control to the origin. Then let's make an offset group by using the create node command to make an empty transform node. Using XForm, we can match the offset group's transforms with our joints. If control had a parent to begin with, then we can parent our offset group to that transform. Next, we can XForm our control to match our control's original translation and rotation. If we have an offset group, we can go ahead and parent our control to it. At this point, if we want the control to snap into place of our joint, we can zero the transforms. If we want our control to not move visually, we can freeze the transforms. Then let's make sure our control's pivot ends up inside of our joint. And at last, let's just make sure the history is removed from our control. I just noticed a couple typos that I want to clean up here. This should be using a lowercase s, and this should use the control rotation variable instead. Because the A to B script isn't sourced yet in our Maya session, we cannot call the function. I'm just going to copy the command from my shelf and use that to import my shelf utils script. Now I can add nmutils to the A to B function here. Okay, I think we're good to start using this now. Let's source our script and hope we don't run into any errors. Let's go ahead and test this out in a few different scenarios. First, I'm going to copy this command for the script twice. Once with snap-align equals false, and once with snap-align equals true. Then I'll create my control and select the joint I want to align it to. Next, I'll run one of these commands here. I get an error because I'm actually in a different Maya session than from before when we wrote reset transforms. I'll just paste that script to the bottom of my editor, then source it. Now when I run this command again, it should work. Let's take a look at our 2 different options here. With snap-align equals true, the control visually moved to the joint and matched its orientation. But if I run this with snap-align equals false, the control doesn't move, but the orientation and pivot still match our joint. Keep in mind, I'm using Maya 2020, so we're using the first condition. Let's see what happens if I align a control to a joint, then parent it to another control. You'll notice that we now have transforms. That's not great. This is because we're using the offset parent matrix, and the control now has a new parent. Not to worry, our script can handle this. We just need to run it again with the control, now a child of the other control. Let's run this again, but this time we'll parent our control into the hierarchy first. When we run this, it works as expected. What's great is we can even pickwalk up this hierarchy. What if we wanted to test the script for 2019? Or let's say we just didn't want to use the offset parent matrix. We could either add some additional functionality into our script, or we could just change the name of our attribute we're checking for. I'm pretty sure offset parent matrix QQQ does not exist, so this condition will be false, and it will use the other option instead. Let's source our function again, since we just changed it. Now let's go ahead and create another control and use our script to snap it to the joint. It works like before, but this time we have an offset group. Let's now try it using the other option. Again, same functionality as before, but with the additional group. Now we can easily parent this offset group to the control above. The transforms are automatically updated, which is fine because we're not concerned about the transforms on these groups, as the animator should not be keying them. Let's do one more test. For this one, I'll parent a control in my hierarchy before running the script. Great, the offset group has been inserted above the control. One downside to this method is when you pickwalk up, you can accidentally access a control group. To be safe, it's good to lock and hide these attributes if you don't want them to be keyed. Alright, that's going to be all for this chapter. I know this is a lot to digest, so congratulations on making it to this point. Before moving on to chapter 9, go through some of the other scripts in the shelf utils Python file. It's also helpful to search online to see what scripts other people have shared. Maybe you have some cool ideas for scripts you could write. If not, try to come up with some, then break it down into steps and try scripting it. As always, thanks for watching, and I'll see you in Chapter 9.